Good morning, everybody. Everybody's awake now. As you can see, antimicrobial resistance can affect anyone at any age in any country. It's not said by me, but it's said by the World Health Organization, the leading organization in the world looking after public health, and who's listed already several years ago antimicrobial resistance as one of the most important risks for human health. Just to tell you that it is indeed an important topic. My name is Jeroen Dewulf, as Philippe already introduced you. I'm working at Ghent University, and we've been looking at the issue of antimicrobial use and resistance in farm animals for many years. We've been looking at the problems related to that, but we also tried to find some solutions. And that's also the way I'm going to build up my presentation this morning for you. First, I'm going to try to explain a little bit what the problem is, where it is, and how large it could become at a certain point. But then secondly, and probably more interesting, I'll also point you out what possible solutions are. So antimicrobial resistance has been looked at as one, as I said before, as one of the most dangerous risks for mankind. And in a rather recent study in the UK, the O'Neill report, for some of you may know it, it was predicted that if we do not stop the epidemic of antimicrobial resistance, I would call it, then it would become a huge problem. It would become a human health problem which is larger than the problem of cancer. Because it can emerge so fast and it can become such a big an issue all over the world. The predictions are, and just be careful, these are predictions, this is for sure not yet the reality today, but if we would not change the ways we are using antibiotics, both in animal medicine and in human medicine, then the predictions are that by 2040, we would have, by 2050, we would have 10 million people dying from bacterial infections that are untreated, that had become untreatable every year. So it is indeed a scary foresight. If you want to see where that would happen, then immediately you see that we are at exactly the right place to talk about this topic here in Asia, because it is indeed in Asia that the biggest casualties are predicted. And why is that? Well, there is one simple reason, and that's of course that the majority of the human population lives on the continent of Asia, so it's not so difficult to get the most casualties there. But secondly, it's also because the problem of antimicrobial resistance is already today in Asia substantially larger than it is in other continents such as Europe or Northern Latin America. So it is certainly here, but also in Africa, a very pressing issue. It's not by coincidence also that those two continents are the ones where the use of antimicrobials is rather lesser regulated than in other parts of the world. So the more antimicrobials you use and the lesser regulated you do that, the more problems you see both in animals and in humans. I'll come back to that. It is a One Health issue, and I know some of you may agree with me that One Health is a buzzword these days. You have to call everything One Health if you want to find research money. At least that's in our world a little bit the case. But I think antimicrobial resistance is truly a One Health issue. It is one of those topics where really animal medicine, veterinary medicine, human medicine, and also the environment come together. We are using antimicrobials in humans. Don't forget, we're using antimicrobials in humans. The problem of antimicrobial resistance in human medicine is largely caused by the fact that we are using a lot of antimicrobials in humans. But we are also using a lot of antimicrobials in animals, both in food animals and in companion animals. Often we forget about those companion animals, but also in companion animals, antimicrobials are used and very often the same types of antimicrobials as are used in human medicine. So in all those fields, we are using antimicrobials. And these fields are not independent from each other. It is an illusion to think that what you do here does not infect this. In the other way around, it's exactly the same. What you do in humans does impact on what you see in animals. And then, of course, we have the environment in between. And we have the wildlife, which is often making a link between produced animals and human medicine or humans. We have the environment where we grow crops, where we grow fruit, and we have, of course, the consumption of animal products. So there's plenty of transmission routes through which we can transmit a resistance from one animal or from one ecosystem to another ecosystem. And notice that the arrows go in both directions. So often we think about a unilateral or unidirectional process, and we often think that resistance goes from animals, at least of the ortho world is thinking about that. The resistance goes from animals to humans and not the other way around, and that's not true. We know that it goes in both directions. In biology, the human species is just another animal species, so there wouldn't be any reason not to understand, not to think that it would go in two directions. Another thing also important in Asia, and probably more in Asia than in the rest of the world, is the production of antimicrobials. Also, the production of antimicrobials causes a lot of waste, which gets into the environment, can get into the water, can get into the soil, and also these wastes can then, through this environment, can get into the animals and to the humans and select for resistance. So it is really the animal, the environment, and the human playing together a role in this whole story. If we want to look a little bit closer into this transmission from animals to humans, we see that there is different ways of transmitting resistance from one side to the other. Of course, we're using antimicrobials in animals, and we're using antimicrobials in humans. As I said before, at both sides, we select for resistance. If we use antibiotics, we select for resistance. Whether we want it or not, it is unavoidable. If you use antimicrobials, you will select for resistance. You can do it a little bit more, a little bit less. I'll come back to that. But it is unavoidable that you select for resistance. One very obvious link between the animal world and the human world are, of course, those zoonotic bacteria. Those zoonoses you all know about. I've been talking about them already at this conference. Salmonella, Campylobacter, some species of E. coli, and others. Of course, if they get resistant in the animal, and then next they are transmitted to humans, they will not lose their resistance genes during this transmission process. If they became resistant, if a salmonella becomes resistant in poultry due to the use of antibiotics in poultry, when this salmonella gets into a human, it will just carry on its resistance genes to the human, and it will become more difficult to treat the patient with antibiotics. That's a very obvious link. It's also a link which has been exhaustively described in literature. There's plenty of studies, plenty of papers showing that indeed if you find those zoonotic bacteria in humans, that you will find the same types of resistance as you will find them in the animal source. However, it's not the only link. Sometimes people, if they think about transmission from resistance from animals to humans, they only think about the zoonosis, and that's where it stops. But it's certainly not the only link, and it's likely also not the most important link. There are others, but before I go into that, maybe first just emphasize that within the animal body, within the human body, and I remember from Philippe's introduction at yesterday morning, there's 100 billion, I don't know, a very big number actually, 100 billion bacteria in the gut, in every gram of the gut. So there's huge amount of bacteria in that gut, and these bacteria do exchange genetic information among each other. And that's what's happening here. There's plenty of commensals in there, and they exchange genetic material with the zoonosis that can be there as well. And by exchanging genetic material will also include the exchange of resistance genes. They will do that to the pathogens as well. I generally refer to these commensals as actually a reservoir of genetic information, especially a reservoir of resistance genes. And whenever the pathogen gets into the animal, it can just go and shop in the reservoir to find the resistant genes that are useful in the circumstances this pathogen is living in. And especially if you then put a selection pressure on it, if you treat the animals with antibiotics, either as a growth promoter or as a treatment, then of course the bacteria, the pathogen, has a good reason to go and shop in the commensal bacteria to find resistance genes to protect itself from this selection pressure. So this exchange of genetic information between these different components, the different types of bacteria, is very important. This happens in animals, and of course it also happens in humans, as I said before, a human is just another animal species. And then of course these commensals are also transmitted. And they are transmitted much more than we transmit zoonosis. If we produce animals in a perfect situation, we can even avoid to have zoonosis. We can produce them without salmonella. It's not so easy to do that without Campylobacter, but at least we can try to control the levels of Campylobacter. You'll never produce a bird without E. coli. It's always going to be there, and it's going to be there in a massive amount. And it's also going to be transmitted up onto the meat, at least at the outside. So during the slaughter process, so if you eat a piece, or if you're in contact with a piece of broiler meat, you will be in contact with bacteria, with commensal bacteria originating from those animals. And in those commensal bacteria, you will find resistance genes. So that is probably a much more important transmission route, at least in terms of frequency of occurrence, than this zoonotic transmission. And so that's probably where the focus should be, on this transmitting of the commensals. There can also be transmission of pathogens, but that would be rather lesser frequent, just because pathogens are generally more species specific. They would not so easily survive in a different gut, but it could happen as well. And then there is the issue of the residues. Residues is very interesting. If we treat animals with antibiotics, and then shortly after that we would slaughter the animals, or we would consume the eggs, then there is a possibility, or it's likely, that we will find residues in the meat or in the eggs or in the milk, if we talk about dairy. And these residues that can then get into the humans, and there again select for resistance. If I give this talk in Europe, I generally say that this is of no relevance, because the fact, for the reason that we are controlling very strongly on these residues. It's a rather easy thing to control. It's just a chemical analysis, and the methods are very readily available to check for these residues in the meat. Our farmers, our veterinarians are very much aware of this. The withdrawal time, it's an extremely important issue. If you use the antibiotics, respect your withdrawal time. Make sure that there is no residues in the meat. But if at some stage it would happen, then still it is likely that there are very, very low concentrations into the meat. The concentrations that are not sufficient to really select for resistance in the human body. So if you control this part well, it's of no importance. If you're living in a part of the world where the control of residues in the meat is much lesser well developed, then this can be an additional selection pressure. Because indeed, if you are consuming meat or eggs that are containing high levels of high concentrations of residues of antibiotics, this can give you an additional selection pressure to select for resistance. So it depends a little bit on where you are and what is the level of control on this. But it is relatively easily to control. In the past, this has been more or less the focus. This has been, at least in Europe and the US, we made our legislations about this. And very often, legislation is about things you can measure. And that's why we've put the focus on the residues, whereas actually the danger is much more here in the resistance. And there is a lot of confusion between residues and resistance. People think that if they can control the problem of residues, that they've also controlled the problem of resistance, which is absolutely not the case. So it's two different things, and you should control both sides. Of course, you have to reduce these residues levels, but once you've done that, you're not yet there. You don't not had solved the problem, because then still there is this problem of transmission of resistance. And again, it can also go in the other way around, as I said before. Just to give you a small example of how easily this transmission through commensals can happen, this is a study we've conducted a couple of years ago in our research group, where we have a system which is mimicking the gut flora of a human being. And in this system, we have introduced a human E. coli here at the beginning of our trial, which then continues to stay there. But more importantly, 1 day later, we have inoculated our model, or 2 days later, we have inoculated our model with a poultry donor, E. coli donor, which was containing the ESBL resistance gene. So extended spectrum beta-lactamase, you probably are familiar with this ESBL resistance gene, which is a broad spectrum type of resistance. So we've introduced that into our model, and most interesting is to see that already 1 day later, at day 3, we had a new bacterium. And that is what we call the transconjugant. That is the new E. coli, which is a human E. coli, but which has acquired this gene from this poultry source. So it's a human E. coli, fully adapted to the human gut flora. It can survive in this human gut flora perfectly, because that is its natural habitat. But it has acquired this new resistant gene. Remember my story about going and shopping in the commensals and try to see what is useful. And this is my new bacterium. It stays there at a rather low prevalence. It's only if you search very well, you'll see it. But a couple of days later, we selected this, we implicated a selection pressure. So it's as if we treated our patients with antibiotics. So we introduced antibiotics into the model, and immediately you see that this transconjugant actually becomes our dominant strain. And that's the one which is again perfectly adapted to the human flora, but which has acquired a resistance gene from animals. So if you think about transmission of resistance from animals to humans, you should rather think about transmission of genes and not so much about transmission of bacteria. The bacteria are only the carriers of the genes. And the genes are the ones that are causing the problems, are the ones that are spreading, and are the ones that are transmitted very easily from one type of bacteria to another type of bacteria and are causing the problems. Often you get this discussion, is this really a problem? Is there really transmission? Or does use of antibiotics in animals, does that really add to the problem of antimicrobial resistance in humans? Well, there's plenty of literature on it, and these days, I would say every month, more or less, a new review paper comes out that has looked into this, and almost always you come to the same conclusion, and it's highlighted here. Overall, there is evidence that the proportion of human extraintestinal extended spectrum resistance E. coli infections originate from food-producing animals. And then I've highlighted this, especially for today. Poultry in particular is probably a source. So if you look into all the literature available, and you add everything, if you bring everything together, the conclusion is, and that's not the only paper saying this, there's plenty of papers coming to the same conclusion. The conclusion is that there is an attribution of what we do in animals to the problem in human medicine. Does that mean that if we would solve the problem in animal production, in veterinary medicine, if we would assume we would stop using antibiotics tomorrow in veterinary medicine, would then immediately the problem in human medicine be solved? Of course not. As I said already in my introduction, the problem of antimicrobial resistance in human medicine is largely due to the use of antibiotics in human medicine, but there is also an attribution from veterinary medicine, there is an attribution from animal production. And so we do contribute to the problem. How much? That's a very difficult question. Nobody today is able to put a number on that. Is it 5%? Is it 10%? Is it 20%? Likely, it's going to depend very much on what type of resistance you're looking at. Some types of resistance are for 100% linked to use in human medicine. Other types of resistance, for instance, the ESBL typically, but also the cholesterol resistance, I'll come back to it later, are probably for much larger part linked to what we do in veterinary medicine. But again, I'm not capable of putting a number on it. But the fact that there is an attribution and it has been proven over and over and over again should be sufficient motivation to work on it. Again, it's a One Health issue. This is a nice study done in the Netherlands where they looked into a review study where they looked into all the literature searching for residues and resistance genes into the environment. And I'm not going to read it out for you, but if you look at here, it says that actually wherever you search into the environment, either in water or in vegetable produced or in the soil, you have a pretty big likelihood to find resistance genes. And so it is really also in the environment that we should never ignore this environment as a very important source of resistance. And last one, a more recent publication on this cholesterol resistance. This is a South American study conducted in South America, where again it was concluded that this MCR1, this new transmittable cholesterol resistant gene, found in humans and actually for the first time described in China, but since then it has been described all over the world, it has been found all over the world, and it says here that what you find in humans is linked to what is present in broilers. So the problem is pretty important. We know that animal medicine, veterinary medicine, animal production has a part in it. We cannot ignore that, so we shouldn't say that it has nothing to do with us. Another question is, where does this problem come from? And to explain this briefly, I always put that separate that in 4 steps. The first step is the emergence of resistance. And actually, antimicrobial resistance is a very old phenomenon. And it's very nicely described in this Nature paper, where they've made drillings into the ice of glaciers. And into this ice, they know that this layer of ice was frozen 30,000 years ago, more or less. And in this ice, they find bacteria. And in these bacteria, they find resistance genes, proving that already 30,000 years ago, there was antimicrobial resistance present. So long before we ever found antibiotics, and certainly long before we ever start using antibiotics, there was already antibiotic resistance present in nature. Is that a surprise? No, of course not, because antibiotics are natural products, so the answer to the antibiotics in nature is also likely to be present there. Antibiotics are natural products, and so the resistance is also a natural phenomenon of bacteria to respond to these antibiotics. However, they are present, these resistant genes are present in very, very, very low prevalences. You need to search very careful to find them. The majority of the bacteria 30,000 years ago you would find would be fully susceptible, and only a very small minority would carry some resistant genes. There's also a very abundant type of resistant genes. There's plenty of resistant genes out there, a huge variety. This also means that if ever, which is pretty unlikely, we would find a new antibiotic to be used in veterinary medicine, then probably already the answer to that new antibiotic is already available in nature, is already out there. So the solution to the problem of antibiotic resistance is not finding new antibiotics and continue doing the way we've done it in the last 50 years. The solution will be to do other things. Bacteria interact with each other. As I told it before, this exchange of resistant genes, which you can see here on the picture, where here there's this conjugation where genetic material will go from one bacteria to another. And this is a very important, in the epidemiology of resistance, this is very important because it means that your resistance will not only go from the mother bacteria to the daughter bacteria, just through the multiplication of the splitting of the bacteria, but it will also spread in a horizontal way from one type of bacteria to another. So once you've selected for resistance in one group of bacteria, then subsequently it can spread to other groups of bacteria pretty easily, as I've shown before. So this exchange and this spread goes very rapidly. Until now, I have not talked about use of antibiotics. So the emergence of resistance is a natural phenomenon. If ever you get into the discussion, this political discussion between veterinarians and human doctors, who is causing the problem of resistance or where is the resistance coming from, the easy answer out the discussion is it comes from nature. And it's actually right as well, because originally resistant genes, they come out of nature, out of the environment. But the next step is the most important one, is the step where you select for resistance, where you will increase the level of resistance. And that is, of course, where antibiotic use will come into the play. This is a study we've conducted also in our group, where we looked at, it's way too small to read, but where we looked at antibiotic use in the x-axis and levels of resistance in the y-axis. And we've done that for different types of antibiotics, and you might be able to read that these are the fluoroquinolones, third-generation cephalosporins, aminopenicillins, and so on. But for every type of antibiotic you find that the more antibiotics you use, the higher your levels of resistance will be. And in this graph, every dot is a country. So this is very highly aggregated data. This is data coming from 7 European countries where we had sufficient data on use and on resistance in animals. And so it's aggregated at a very high level. So the dots, behind every dot, there is a huge amount of data, individual country data. And you see that for every country, we find the same association. The higher your use, the higher your levels of resistance are. That was published in 2014. 1 year later, ECDC, EFSA, and EMA published their first GIRACRA report. So these are the European research institutes that are looking at human health, animal health, and medicines use. And they found very, very comparable associations. This is again for fluoroquinolones and for Campylobacter, a relevant bacteria for poultry production. And here again, you find this positive slope. The more antimicrobials you use, the higher your levels of resistance are. And again, every dot is a country. There's more countries in this study. Similar patterns were found for tetracycline resistance, macrolide resistance. And whenever you have enough data, you will find this type of associations. Going back to our first study, if you want to know which are the countries, well, they are up there. And this is my country. I'm absolutely not proud of that. We are, at that moment, we were, of those 7 countries where we had enough data, we were the one using the highest amount of antimicrobials, and that was translated also in the highest level of resistance. And we have a very remarkable good fit here. It's really fitting very well. The more you use, the higher your level of resistance is. Countries that have a long-standing tradition of very moderate use, of very low use of antibiotics, they have also a very moderate level of resistance in animals. So it's really mirroring each other pretty well. Just for the to be politically correct, again, these were the countries at that time where we had enough data. If I would add some other countries here, I think, and maybe here is Thailand and China, and I don't know, but probably we would go way up. So just don't think that after this slide that Belgium is the worst country in the world, at least not for antimicrobial usage. So I mean, there is others where the usage is even much higher. This is new data. It's not in the slides in your book because it's only recently added and it's not published yet. And this is data coming from the EU effort project. It's a very large project from the European Commission, where we're looking at antimicrobial usage in 9 European countries. And this is usage in poultry production in 9 European countries, where we measured the usage in exactly the same methodology, because that's often a tricky thing. If you're measuring usage, there's plenty of different methodologies available, and everybody does it a little bit different to avoid that you can compare one country with another. Here we've done it exactly the same in all the countries, and you see that there are some countries that have very, very low use in the broiler productions, and there's other countries that have much higher levels of use. So what is this number saying? Well, if you have, I'll take Belgium here, if you have a treatment incidence of around 100, this is the median, around 100, it means that if you have 1,000 animals, daily 100 would be used with, would be treated with antibiotics. Of course, that's not the way it works, so you'll treat the whole group always, but it means that if a broiler would live for 1,000 days, it would be treated 100 days out of those 1,000, 10% in other words, of its lifetime, it would be treated with antibiotics. So in some European countries, it's 10%, some countries it's 1 or 2%, and some countries it's 20%, and in some exceptional cases, it even goes much higher. It goes up to 100 and even above 100%. And that's when you apply 2 or 3 treatments at the same time, it would add up, and it would be as if you would treat your animals more than the total lifetime. Again, this is in a circumstance where we do not use any growth promoters. If you would do this study in countries where they still use growth promoters, you would be all up here around this 1,000, around 100%, because then you almost continuously are applying a selection pressure and using antibiotics. So even for those countries in Europe that are not doing so well, it can still be much worse than this. Also from this study, and there's a lot of numbers here, but I'm going to help go through this together. This is the types of antimicrobials used in broiler production in the different European countries. And just look at this. These are the fluoroquinolones and the polymyxins. So polymyxin, this is exclusively cholesterol. Well, and then you see both are CIAs. What are the CIAs? Those are the critically important antimicrobials. By the list of the WHO, they rank the importance of antimicrobials, and the most critically important are the 3rd and 4th generation cephalosporins or fluoroquinolones. And recently, due to this cholesterol resistance problem, cholesterol has been added to this list, has been promoted, if you want, to the most important, most critical. And then you see that a lot of the antimicrobials we're using in broiler production are actually belonging to this most critically important. But even more interestingly, you see, if we take polymyxins, some countries are using a lot of them. For instance, Italy, half of the antimicrobials used in Italy are polymyxins, whereas other countries, the Netherlands, Belgium, don't use polymyxins at all. Do we see totally different types of pathology in those countries? No. We see very, very, very comparable type of pathology. But we're using totally different types of antibiotics and totally different levels of antibiotics. For instance, if you look at the Netherlands and Denmark, two countries that are doing very well in terms of limited antibiotic use. Denmark, for instance, they're only using lincospectin and the tetracyclines, whereas then tetracyclines by the other countries are used much lesser. What I want to bring as a message here is that antibiotic usage is not very much linked to the type of pathology you are encountering. Antibiotic usage is very much linked to tradition, probably to marketing, and other motivators to select one or the other antibiotic, and not necessarily really based on truly veterinary investigation that tell you based on bacteriology and antibiograms that this or another antibiotic has exactly the right spectrum to be used. There's plenty of other reasons, probably the price, the availability, and things like that will have a much bigger influence than true veterinary reasoning. If you look in literature, there's a little bit of data on resistance in Asia. It's not very abundant, so those of you that have ambitions, this is really a field where you can do a lot of research in Asia, because we don't have so much data, both on the usage and the resistance side. But what is available is this review paper on resistance, and the red bars, so these are different types of antibiotics, and the red bars are the resistance levels in broilers, in chickens in different Asian countries. So it's coming from Vietnam, Thailand, Vietnam, Indonesia, and some Chinese data in there, I think. So you see that, of no surprise, that the levels of resistance in Asia are very, very high. This is substantially higher than what we would see in European data. And of course, this is again linked to the usage. Okay, once we've selected for resistance, will it then, if we stop using it, what will happen? Well, often what we see, and this is an example of pigs, but what we see that if we stop using a certain antimicrobial, that your resistance will continue to be present. This is the example of chloramphenicol. We've stopped using that 30 years ago in Europe, and still the resistance against chloramphenicol is abundantly present. And so you select for resistance very easily. Getting rid of resistance goes much slower and is much more difficult. Can it never go away? And from now on, I'll start with the positive side of my talk. Can it never go away? Well, it can go away. And the good example is, for instance, again, Belgium. We have been working in reducing our antibiotic use in the last years substantially. In the last 5 years, we've reduced the total use of antibiotics in animals with 20%. And positively, we also see that this translates into a downward trend in levels of resistance. Since we've started reducing our use, we do see, with some delay, 1 or 2 years of delay, we see that our levels of resistance are also start to go down in our commensal bacteria. So that's a very positive message for everybody. It's not a lost case if you can bend the curve, if you can, instead of, because before it was all going up, but if you can bend the curve in use, you will also be able to bend the curve in your resistance. So what can we do about it? I think the message is pretty clear from now on. It's all about using lesser antimicrobials. We should avoid to use antimicrobials, and then it will result in less resistance. But obviously, we cannot do that at the cost of a reduced production levels. Because if I would tell you just stop using antimicrobials, and I don't mind if you have 20% mortality, or if your birds will grow 10% lesser fast, nobody would ever listen, and they would say, well, this is totally impossible, end of the story. So we need to find improvements that can help you without having a negative effect on the production. And a lot has been said already at this conference about improved feed, and especially about feed additives, and I will not talk about that because it's not my field of expertise. So I will talk about another possibility. Not with the pretension to say that this is the best one. I would rather see it as an addition. It's not either feed additives or biosecurity, but it's much more the combination. You need better feed, you need probably some feed additives, and you also need improved biosecurity. And that will be the focus of my story. So if I talk about biosecurity, I talk about the combination of measures taken to reduce the risk of introduction and spread of diseases into a herd. I will focus on the herd level. So maybe just focus on the fact that it has two components. It's the risk of introduction and the risk of spread. And we translate that into the external biosecurity and the internal biosecurity. External biosecurity is everything you can do to avoid the risk of introduction, to seal your farm from the outer world. The internal biosecurity is everything you do to avoid the continuous spread of bacteria, of pathogens, whatever, viruses, in your farm. That's the internal biosecurity. And we look at biosecurity as the fundament, the basis of any disease preventive measures. If you don't have good biosecurity, if you're working in dirty stables, if you're working with poor management, you can add as much feed additives as you want, you can add as much vaccines as you want, they will have a poor effect. If you do that in very good conditions, you will just increase your effect, you will have a synergistic result. What we did when we start studying the biosecurity, I think more than 10 years ago, the first problem we encountered, and that's a problem everybody encounters, is that it's difficult to measure. If you're an experienced vet, if you go on many farms, you will come into a farm and you will say, this is a good farm. This has a good biosecurity. But if I ask you to translate that into a number, from 0 to 10 or from 0 to 100, whatever type of number, it's not easy. Is this a 6 out of 10 or is this a 7 out of 10, 5? It's not so easy. So that's what we try to do here with this tool, where we try to quantify biosecurity based on a questionnaire. And the good thing about once you've quantified it, you make it measurable. And once something is measurable, you can start to improve on it. And the fact that if you quantify biosecurity, you can compare scores between different herds, but you can also compare the score of one herd over time. If you look over time, you do the scoring today, you come back within 6 months, within 1 year, and see how the score has evolved. And you take different risks into account. That's what we did in our scoring tool. It's a risk-based scoring tool. So it's a lot of questions you have to fill in. But it's not just a 0-1. It's not just, well, I mean, the answers are yes, no, but behind the answer, there is a calculating system. There is an algorithm that will take into account the importance of the different questions. Some measures are much more important than others. So some will get high points and others will get lower points. So that's what behind it. And if you look into the biosecurity score for broilers, which is so we have it for pigs and broilers, and we are currently developing it for cattle. It's almost ready. But for broilers, we have this external biosecurity with the different subcategories. I'm not going to read them out for you one by one, but you can easily see them. And you see that these different subcategories, they get different weight factors. Some are more important, get higher weights than others. And the same holds true for the internal biosecurity. Right? And in broilers, 70% of the score goes to the external, 30% of the score goes to the internal. In pigs, it's a 50-50% distribution. So that depends a little bit on the production system. So you get the scores, and at the end, if you fill in this questionnaire, you'll get a score from 0 to 100. So what I previously asked you, can you give me a score for this farm? Well, with this tool, you can. You'll get something of your internal biosecurity has a score of 65. And then we know relatively accurate what the level of biosecurity is. And at least it's reproducible. It's not necessarily a perfect measurement. For every measurement, you can say maybe I would put the score a little bit higher or lower. But anyway, it's a reproducible way of measuring the biosecurity. And from that point onwards, you can start working. You also get your subcategories. will immediately see, okay, I score pretty high on purchase of animals, but I score very low on vermin and bird control. Or I score very low on hygiene and cleaning. And then immediately you can also see on this specific farm, this is the topic we should advise upon. This is the topic we have to work and we have to improve. This is our website, how it looks currently. The questionnaire has been filled in 4,000 pigs and more than 1,000 broiler farms already. It's available in Dutch, in English, and recently also in Chinese. So the Chinese among you, we have translated the website fully also into Chinese. And it's used, so the biocheck scoring system for broilers is already used in 40 different countries. It means that we can also provide you with averages from your country. So if you have, if we have enough data, your farm will not be compared to the average of the world, but it will be compared to the average of your specific country, which makes it even more relevant, of course. I'm not going into this scores due to lack of time, but you see a lot of variation. Some parts are scoring pretty high on average, others are scoring relatively low. It's always the case that there are things that can be improved. Even on the best farms, there is still margin for improvement, and this is a very easy tool to help you. Which I haven't said yet is that this is totally free for use. It's without any payment, and it's accessible for everybody. You just go to the website and you can start using it, and we don't charge you anything. The only thing we're charging you is that the data, in an anonymous way, we don't need to know the name of the farm or the address, but in an anonymous way, the data comes to us. So for us, this is a cheap way of collecting information, and for you, it's a cheap way of using the tool. Finally, my last slide. We've used this system to advise farms, and that was a study done in Belgium, to advise farms on improvement of biosecurity. And you see that we've improved the biosecurity with a little bit, some improvements, a change of 5 points for external, 4 points for internal. That's not massive, that's not spectacular, but it did change something in the farms. We had some changes in mortality in the first week, went up a little bit, but the total mortality went down. The feed conversion went down a little bit, the performance index went up, but most importantly, and that's my talk about, we were able to reduce the usage of antibiotics with almost 30%. So 30% lower use and still a better performance of the flocks. And this, we are currently trying to repeat the study again in several countries, and we've done this in pig production in a much bigger type of trials, and repeatedly again we found this type of results where we are, by improving biosecurity, we are capable of improving the production results and at the same time reducing the levels of antibiotic usage. So that's the end of my presentation, and I'll thank you for your attention.